Bismillahirrahmanirrahim. Today our lecture is about heat exchanger designing modeling by using Aspen Plus. Today we do a simulation about heat exchanger. After doing this, you will be able to learn about procedure designing heat exchanger using shortcut method, using rigorous method, detailed shell and tube heat exchanger. Before doing a simulation of heat exchanger, first we do a brief study about different exchangers in Aspen Plus. Here, click on New, click on Chemical Process, Specialty Chemical with metric units, Create, go in Simulation Environment. Click on exchangers. Here we have first heater, second heat X, third multi-heat exchanger, and fourth is HX flux heat exchanger. First we do a brief study about these four types of heat exchangers in Aspen Plus. First we do study about heat exchanger model in Aspen Plus. First heater, simple. This heater, simple type of heat exchanger called heater. It is a basic heat exchanger, performed simple energy calculations, required one process stream. In a heater, just required one process stream in and one process stream out, and it is used to calculate heat duty for different fluid. Second, we have heat exchange. Second heat X in Aspen Plus. It is used to calculate energy balance, different pressure drop, velocities, and so on. It is required two process streams, hot and cold, wide variety of shell and tube heat exchangers. It is used to calculate mechanical vibrations, calculate fouling estimation. It is generally used for designing calculations, and it is performed heat transfer tasks like countercurrent and co-current exchangers, TEM type exchangers, double pipe and multi-tube exchangers, single and double segmental baffles, rod baffles, and unbaffled heat exchangers. And third, we have MH heat exchanger. Simply, it is used to transfer heat between multiple hot and cool streams. It is used multiple blocks and streams. And fourth, we have HX flux. HX flux heat exchanger perform heat transfer between sink and source using convective heat transfer. It is not required input and output material streams. Determine like driving force, long LMTD, long mean temperature difference. It is used to determine driving force. It is used to found unknown variables using rigorous method. Okay, now we move toward our task. Today we do our workshop about heater. Here we have example Freon 12, more commonly referred as R12. It is introduced to a shell and tube heat exchanger flow rate of 12,000 km/h. This fluid needs to be heated from 50 degree Kelvin to 300 Kelvin and pressure 8 atm using ethylene glycol as a hot source, which is available at 300 Kelvin. The heat exchanger to be used for this purpose is made of carbon steel tubing with a pressure drop that should not be exceed 5 psi or 0.1 bar for either the shell or tube side, and calculate amount of heat duty. Here we are using heater and to calculate heat duty. Okay, first we want to know about heat duty. Heat duty, rate of heat transfer required. Heat duty is based on the amount of energy that must be transferred between two fluids. It is essential parameter for heat exchanger design. Two main methods which we physically use to calculate heat duty of different fluids in heat exchanger. Q is equal to mcp del T, and second is Q is equal to UA del T Lm. Okay, now we do our experiment according to our example we have here. Now we do our experiment. So first we add our components, click on components and add e.g. ethylene glycol and R12, and now move toward methods. Here we are using simple method. Click on method options, and here we are using NRTL method because we have pressure of our fluid below to 10 bar, so that's why we are using NRTL method. Now we want to check binary interactions between these two components, so click on parameters and click on the NRTL method. Here you see no binary interactions are available between these components. So if we want to check binary interactions between these components, so click on estimate by using unifac, click on reset, and now click on next to perform property analysis setup. Here you have to see binary interactions coefficients are available between ethylene glycol and R12, like here. Okay, go in simulation environment. Here results are available. Click on exchanger. Here we are use here simple heater to calculate heat duty. First we resize it, and now we give it material streams. First inlet, second outlet, then rename of heat exchanger. Okay, now we add compositions and operating parameters of inlet stream are 12 in, and here are 12 out. Okay, double click on inlet stream to add operating parameters and composition of inlet stream. Here we know that we have temperature 250 degree Kelvin and pressure 8 atm. 250 degree Kelvin and 8 atm pressure, and we know mass flow rate 2000 kilogram per hour. 2000 kilogram per hour, and we are here using R12, and here click on mass fraction. So click on run. Here we are adding composition and operating conditions of block like heater. We have temperature at inlet stream 250 100 degree Kelvin, and at outlet we have temperature 300 degrees Kelvin. It means the temperature change here 50 degree Kelvin. So click on temperature change. Here temperature is 50 Kelvin, and pressure drop. Here we are writing minus 0.1 bar. It's mean pressure drop here 0.1 bar drop in Aspen plus negative sign show that pressure drop, and positive sign show outlet pressure. Here we see blue tick, so click on next to run our simulation. Okay, here see results are available. See at bottom of the Aspen Plus, results are available, no error occurs. So go in a simulation tab, in a blog tab sites, click on results. So here outlet temperature is, first if we calculate in Kelvin, 300 degrees C. Our inlet temperature is 250 degrees Kelvin, and outlet temperature is 300 degrees Kelvin. Okay, outlet pressure in bar 8 bar, and heat duty you will calculate in different units per hour, and pressure drop here 0.1 bar. Okay, here see no error or occurs between our simulation process. So simulation of simple heater is complete. In our next lectures I will do simulation in a heat X, in a MX, M heat X, and HX flux.